The example is, I'll be completely honest with you, designed to be a dramatization. Okay? Elzar Petizauer worked a long time, I'm told, on the correlation matrix that gives these results. It's not extremely common, but it does highlight what can happen. The way we get all of these analyses, so this just describes things the same way we had them before. Analyze regression linear. You still put the variables in, but now you change what method. So that instead of enter or delete to get a full model and a reduced model, we're talking about putting in forward or backward or forward stepwise. You can vary the criterion to bring things in and out of the model. You want to set your entry criterion at 0.05. That's tradition. 5% type 1 error. You want to set the removal slightly higher. If you have them both set at 0.05, you can get into an infinite loop where you throw a variable out, you bring the same variable back in, then you throw that variable out. You don't want to do that. And SPSS, I think by default, sets this at 0.10, which means you can accumulate non-contributing predictors at sort of a frightening rate. We're not going to argue too much about a 0.05 versus a 0.055. But a 0.05 and a 0.10, even I get a little weird there. So here it is. The first variable entered was GRE quantitative. We get an R-square of 0.37, which is statistically significant. Over here it lists the variables that are in the equation. Notice it lists GREQ. That t-test squared is that f-test, and the only variable in the model is contributing. It then lists the variables not in the equation, and what it lists for each variable is what the contribution of that variable would be if it were the only second predictor in the model along with GREQ. So beside GREV here it says, what would happen with GREV if the model were GREQ and GREV? Does that make sense? And we can see that GREV would contribute, MAT would contribute, average rate would not contribute. So we've got two candidates for inclusion. The one that will contribute the most is the one with the largest semi-partial. Now it actually gives partials, and it really is a partial, not a semi-partial. And there's somebody did some work, one case in 8,000 or 9,000, where you might get a different result if you actually computed the semi-partial instead of the partial, but this is easier and they're lazy. So MAT would go in next because it's got, of the two that are significant, where they did contribute, it's got the largest multiple semi-partial. So it will lead to the larger R-square. Sure enough, there it is. And so now we have GREQ and MAT that are in the model. And we can see that neither GREV nor average rating would contribute if they were added. So we stop. And notice, if you will, that GREQ is now over-included. Once we put MAT in, the variable that started this whole thing, the one that has the highest simple correlation with the criterion, is no longer contributing. So even in a two-predictor model, you can have over-inclusion. Backwards. Backwards starts with everything in the model. We got an R-square that's statistically significant, but remember, that's dangerous because it's entirely possible to have a full model that has had null washout, and the full model isn't significant, at which point it will stop and it will say there is no model out there. And saying that the full model has null washout and there's no model out there aren't the same thing. Well, we can see that average rating is a candidate for being thrown out, and GREV is a candidate for being thrown out, because neither of those would contribute. We're going to throw out average rating, because there's a 70% chance that that's a type 1 error, and there's only a 14% chance that GREV is a type 1 error, so we're going to throw out average rating. When we throw out average rating, we can see that GREQ is the only candidate for exclusion, so we throw that out. And when we're left with just MAT and GRE, we see that they're both contributing. But notice what happened to GREQ. If at this point GREQ were put back in, it would contribute. So in just a two-predictor model, we also have under-inclusion. Well, let's avoid both of these problems and go with forward stepwise. The first thing in is GREQ. And then both GREV and MAT would contribute if they were put in. MAT will contribute most, so that's what gets put in. Once they're both in, we have to pull GREQ out because it's over-contributing. It's over-included. Over-contributing. It's over-included, so we pull that out. And after we pull that out, leaving us with just an MAT model, nothing will add to the MAT model. Nice little four-predictor example where forwards, backwards, and stepwise all give different answers. You don't find this most of the time. Most of the time, you tend to find something pretty close to convergence, except for over-inclusion with the forward and under-inclusion with the backwards.
Cal,
Yes?
do you decide the over-inclusion by the significant t-value?
Yes. Yep, that puppy's not contributing. All right, so these are designed for predictive modeling. There's no guarantee that they give you the model, even if all you're looking for is an efficient predictive model. There is, however, a really nice use for one of these models. I use it a lot for both predictive research and descriptive research. After I'm done testing hypotheses, did everyone hear that part? After I'm done testing my a priori hypotheses, what I usually like to do is to take my model and play forward with it. What I'll do is I will, on step one, put in the model that I like best. Whatever model I'm going to interpret, whatever model I'm going to hold up and say, this is the best I got for you at this point. Put those predictors in. Then, click on Next, and in block 2 of 2, I put all the other predictors I have in there and click Forward. You with me? So first it's going to take the model that I've built that I like, and then it's going to ask if there are any other variables that, if added to the model, contribute to that model. And every once in a while, I get something new to think about. Now, I will be honest with you. I never confess, certainly not in a published article, that these to this post hoc adventure. Okay? Usually don't even make it part of what gets reported. It's just now something in my head that I use for that next piece of research. Here's the model that I liked. Here's the model that I talked myself into theoretically, and I got an answer of whether it works or works better, poor, da-da-da-da-da. And now I have this opportunity for nagging little thoughts about other variables that, if in the model, increase the fit of the model. And usually, those variables that go in, because I'm using forward, not forward stepwise, something that gets in will often make something that was in there no longer contributing. Now I have not only variables to think about, but collinearity patterns to think about. And here's the really depressing and wonderful part. How can it be both? Here. Usually when I go reading for that variable in the literature, I find something that I've missed. I find somebody who has looked at or thought about that variable or something correlated with it, and I now have a theoretical and a data-driven reason to be interested in that variable. Of course, I cite the literature as the basis for wanting to think about it in the next set of models. Okay? So that's one really nice application, is taking whatever model you've talked yourself into, throwing everything else in, and asking, what have I missed? What variable, if added, would contribute, and what variable, if added, changes the structure of the model I've talked myself into? Okay? It's a very good use of a dangerous technique.